Right now, drifting through the darkness between the stars, there are planets, not orbiting anything, not caught in the gravity of any sun, not warmed by any stellar light, not part of any solar system. Just planets, alone, cold, invisible against the black of interstellar space, moving through the galaxy at the velocities imparted by whatever catastrophe flung them from their original systems. We call them rogue planets, free-floating planets, orphan worlds. The names all carry the same implication: something that was once part of something larger, something that was once in a system, in a relationship with a star, perhaps with other planets, perhaps with moons, and is now alone. Nobody knows exactly how many of them there are. Estimates range from hundreds of billions to possibly as many as trillions in the Milky Way alone. Some analyses suggest there may be as many free-floating planets as there are stars, that for every sun shining in the night sky, there is a dark, starless world drifting somewhere in the darkness between them. Most of these worlds are barren, cold beyond any cold that Earth has ever experienced. Their surfaces, if they have solid surfaces, are at temperatures close to absolute zero, frozen solid, blasted by the cosmic radiation that permeates interstellar space without the protective shield of a stellar magnetic field. Most of them, but not all. In February 2026, a team of scientists from Ludwig Maximilian University of Munich and the Max Planck Institute for Extraterrestrial Physics published a study that changed the way astronomers think about what rogue planets might carry with them. Because some rogue planets have moons, and some of those moons, according to the calculations in this paper, could have liquid water oceans. Right now, in the darkness between the stars, this is the story of what might be living out there, in the places we never thought to look, in environments we never expected to be habitable, drifting through the galaxy in the dark. To understand why a moon orbiting a rogue planet might be habitable, you first need to understand how rogue planets are created. Because they are not formed in the darkness they now inhabit. They were born in solar systems around stars in the same way that planets like Earth were born, from the disk of gas and dust that surrounds a young star as it forms. Planet formation is a chaotic process. The disk of material around a young star is turbulent, dynamic, and full of interactions. Dust grains collide and stick together to form larger aggregates. Those aggregates collide and merge to form planetesimals, kilometer-scale rocky bodies. Planetesimals collide to form protoplanets. Protoplanets merge into planets. Throughout this process, gravitational interactions between the growing planets can be violent. Young planetary systems are often unstable. The gravitational tugs between multiple planets, between planets and the star, between planets and the disk itself, can drive orbits to intersect, to amplify, to produce close encounters that change trajectories dramatically. In some cases, these gravitational encounters result in a planet being flung outward, not onto a wider orbit within the system, completely out, accelerated beyond the escape velocity of the star, launched into interstellar space at whatever velocity the gravitational slingshot imparted. This process is not hypothetical. We have models of the early solar system, the NICE model and its successors, that invoke exactly this kind of early dynamical instability to explain the current configuration of the outer solar system. These models predict that the young solar system had more giant planets than it does today, and that some of them were ejected during the chaotic early period. The solar system may have flung planets into interstellar space billions of years ago. And the same thing has happened in billions of other stellar systems across the galaxy over the full 13 billion years of galactic history. The result is a vast, dark, invisible population of wandering worlds spread through the spaces between the stars, ejected from their birth systems, carrying whatever they had, whatever moons, whatever rings, whatever atmospheres, when they left. And here is the thing that the February 2026 paper focuses on. When a planet is gravitationally ejected from its system, the moons it carries do not necessarily escape with it cleanly. The violent gravitational encounter that ejected the planet also perturbs the orbits of its moons, stretching them from the circular or near-circular orbits they might have had into more elongated, more elliptical shapes. that stretching, that orbital eccentricity, turns out to be a potential lifeline. Because orbital eccentricity is the engine of tidal heating. Let's talk about tidal heating, because it is the central mechanism of this entire story and it deserves careful explanation. Tidal forces arise whenever one body is in the gravitational field of another. The side of a body closer to the gravitational source feels a stronger pull than the side further away. This differential pull, the tidal force, stretches the body slightly in the direction toward and away from the source. For a moon in a circular orbit, the tidal deformation is constant. The moon is always stretched in the same direction, toward and away from the planet, and the deformation does not change as the moon moves around its orbit. No energy is transferred. No heat is generated. The moon simply sits in its tidally deformed state and orbits. For a moon in an elliptical orbit, everything changes. In an elliptical orbit, the moon is not always the same distance from the planet. It swings closer at one end of its orbit and further away at the other. As it swings closer, the tidal force increases and the moon is stretched more. As it swings further away, the tidal force decreases and the moon relaxes. The shape of the moon changes continuously throughout its orbit, squeezing, stretching, squeezing, stretching over and over again with every orbital period. This continuous change in shape requires energy. The internal rock and ice of the moon is not perfectly elastic. It resists deformation, and the energy required to overcome that resistance is converted to heat. Tidal heating. The mechanical energy of the moon's orbital motion is gradually converted into internal thermal energy. This process operates in our own solar system. Jupiter's moon Io, the most volcanically active body in the solar system, is heated almost entirely by tidal forces from Jupiter and from the gravitational resonance with neighboring moons Europa and Ganymede. Io's surface is covered in active volcanoes, sulfurous lava plains, and mountains built by the constant flexing of the moon's interior. The heat generated by tidal forces keeps Io's interior partially molten and its surface geologically hyperactive. Europa, further from Jupiter, receives less intense tidal heating. But the calculations suggest that the tidal heating Europa receives is sufficient to maintain a liquid water ocean beneath its icy outer crust. An ocean that may be 100 kilometers deep, containing more liquid water than all of Earth's oceans combined. Whether anything lives in that dark, pressurized, cold ocean is one of the most anticipated questions in the search for life in the solar system. The February 2026 paper asks a more distant version of the same question. Not whether Europa has life, but whether moons orbiting rogue planets, moons with no stellar light, no external warmth, nothing but the tidal forcing of their parent planet, could be warm enough for liquid water. The answer the paper finds depends on two things: the amount of tidal heating and the ability of the moon to retain that heat. Let's talk about the second problem, because tidal heating alone is not enough. If you generate heat inside a moon, but that heat radiates away into space faster than it is generated, the surface remains cold. The ocean freezes. Life is impossible. For a moon orbiting a rogue planet in interstellar space, the surrounding environment is extraordinarily cold. The temperature of interstellar space, set by the cosmic microwave background, the residual radiation from the Big Bang, is approximately 2.7 degrees above absolute zero. That is colder than anything on Earth's surface by an enormous margin. If a moon's atmosphere were thin, the surface would cool quickly toward this background temperature. Even with tidal heating providing internal warmth, the heat would radiate away through the thin atmosphere into the surrounding cold. This is where the atmospheric composition becomes critical. Earlier models of rogue moon habitability had assumed that the insulating layer would be provided by carbon dioxide, the same greenhouse gas that warms Venus to its extreme temperatures and contributes to Earth's surface warmth above what it would be without any atmosphere. But the February 2026 paper identifies a critical problem with the carbon dioxide model in the extreme cold of interstellar space. Carbon dioxide freezes at a temperature of approximately -78 degrees Celsius under Earth normal pressure. In the extreme cold of interstellar space, with no stellar heating to maintain atmospheric temperatures, the carbon dioxide in a moon's atmosphere would eventually freeze out entirely, condense from the gas phase onto the surface as dry ice, collapsing the greenhouse effect and leaving the surface exposed to the full cold of interstellar space. The calculation in the earlier models showed that a carbon dioxide atmosphere could sustain surface liquid water for approximately 1.6 billion years before the carbon dioxide froze out and the habitability window closed. 1.6 billion years sounds long, and by human standards it is. But 1.6 billion years is not enough by the standards of what we know about the evolution of life. Life on Earth first appeared approximately 3.8 billion years ago, very shortly after the planet formed. But complex multicellular life, the kind of life that builds shells and skeletons and eventually brains and eyes, did not appear until about 600 million years ago. It took 3.2 billion years of microbial chemistry before anything macroscopically complex emerged. If a rogue moon's habitability window closes at 1.6 billion years, it may be long enough for microbial life to appear, but probably not long enough for complex life to emerge. The February 2026 paper proposed a different atmospheric composition, one that does not freeze out in the cold of interstellar space, one that can maintain its greenhouse effect indefinitely. Hydrogen, molecular hydrogen, the simplest molecule in the universe, two hydrogen atoms bonded together, does not freeze at the temperatures of interstellar space under realistic atmospheric conditions. Its freezing point under normal pressure is minus 259 degrees Celsius, extraordinarily close to absolute zero. A hydrogen atmosphere would not condense out of the gas phase and collapse, even in the extreme cold of interstellar space. And hydrogen is an effective greenhouse gas, though through a different mechanism than carbon dioxide. Hydrogen molecules can absorb and re-emit infrared radiation through a process called collision-induced absorption. When two hydrogen molecules collide, the brief collision pair can absorb a photon that neither molecule alone could absorb. In a dense enough hydrogen atmosphere, this collision-induced absorption provides significant greenhouse warming. A thick hydrogen atmosphere on a rogue moon could trap the heat generated by tidal heating and maintain surface temperatures above the freezing point of water, even in the complete absence of any stellar light. The February 2026 calculation showed that a moon with an Earth-like mass, orbiting a rogue planet with sufficient orbital eccentricity to generate adequate tidal heating, wrapped in a thick hydrogen atmosphere, could maintain liquid water on its surface for up to 4.3 billion years. For 0.3 billion years. That is longer than the Earth has existed. It is longer than the sun has been shining. It is long enough, in principle, for the full trajectory from the first self-replicating chemistry to complex multicellular organisms to have played out. The same journey that happened on Earth in the dark, in the cold of interstellar space with no sun. The cradle of life, as one of the study's authors put it, does not necessarily require a sun. Let's sit with that for a moment, because the implications are staggering. The standard picture of the search for life in the universe is organized around stars. Habitable zones, the regions around stars where liquid water can exist on a planetary surface, given a certain atmospheric composition, are defined by stellar luminosity. We search for planets in the habitable zones of other stars. We categorize stars by their type and luminosity and calculate where their habitable zones fall. The entire framework of astrobiology is built around the assumption that stellar light is the energy source for life. And stellar light is an excellent energy source. It is abundant, it is reliable on billion-year timescales, and it drives the photosynthetic chemistry that powers most of the biomass on Earth. The connection between stars and life seems natural, almost inevitable, but it is not the only possible connection. Life on Earth does not exclusively use stellar energy. Deep-sea hydrothermal vents, cracks in the ocean floor where geothermally heated water rich in dissolved minerals emerges into the cold, deep ocean, host ecosystems that operate entirely on chemical energy from the Earth's interior. No sunlight, no photosynthesis, just chemistry, driven by the temperature and chemical gradients between the hot vent fluid and the cold surrounding water. These hydrothermal vent ecosystems were discovered in 1977, and they were immediately recognized as potentially significant for astrobiology. If life can thrive in total darkness at the bottom of Earth's ocean, powered entirely by internal geological processes, then stellar light is not a prerequisite for life. Internal energy sources can sustain biospheres. Tidal heating is an internal energy source. It heats the interior of a moon from within, just as radioactive decay heats Earth's interior and drives the geological processes that power hydrothermal vents. A tidally heated rogue moon would have a warm interior, potentially warm enough to maintain liquid water in a subsurface ocean even if the surface is frozen, and potentially warm enough to maintain liquid water on the surface itself if the atmosphere is thick enough. And the February 2026 paper goes further. It suggests that the surface of such a moon, with a dense hydrogen atmosphere maintaining surface temperatures above the freezing point of water, could have open liquid water oceans. Not a subsurface ocean beneath kilometers of ice, like the proposed ocean of Europa. A surface ocean, a world with actual oceans, actual weather, actual liquid water dynamics, in the dark of interstellar space with no star anywhere nearby. Imagine standing on such a world. The sky above you, if the atmosphere were transparent enough to see through, would be black. Not the black of a clear night sky filled with stars, but truly black. The stars would be visible, perhaps, as faint points of light at the greatest distances. But no sun, no moon-like body illuminating the surface. Just the faint, diffuse starlight of the galaxy's background, and the glow of the planet you orbit, reflecting whatever faint illumination the stars provide. The ocean around you would be dark. Not dark the way Earth's ocean is dark in deep water. Dark because there is no sun to illuminate even the surface, but liquid, moving, perhaps with tides driven by the orbital dynamics of your world and the planet it circles. The atmosphere above you would be thick, warm by the standards of surrounding space, opaque to your eyes in ways that depend on its exact composition. And in that ocean, in that warm, dark, chemically active liquid water, something might be swimming. Let's talk about the numbers, because the question of how many rogue planets there are in the galaxy is central to understanding how significant the February 2026 paper's implications might be. Detecting rogue planets directly is extraordinarily difficult. They emit no significant visible light. They are not hot enough to glow in the way that stars glow, or even in the way that very young gas giants glow with the residual heat of formation. They are dark objects moving through dark space, and they do not gravitationally lens background stars except when they happen to pass very close to our line of sight. The technique of gravitational microlensing, detecting the brief brightening of a background star as an intervening mass passes in front of it and bends the path of the star's light, is the primary tool for detecting rogue planets. When a rogue planet passes in front of a background star from our perspective, the star briefly brightens in a characteristic way. The duration and shape of the brightening encodes information about the mass and distance of the lensing object. Surveys using microlensing, particularly the MOA survey in New Zealand and the OGLE survey in Chile, have detected numerous short-duration microlensing events consistent with Earth mass to Jupiter mass free-floating planets. Statistical analysis of these detections, combined with models of the galactic population, has produced widely varying estimates of the total rogue planet population. The most widely cited estimate from a 2011 paper based on MOA survey data suggested a population of roughly 2 Jupiter mass rogue planets per main sequence star in the Milky Way. If the Milky Way has approximately 200 billion main sequence stars, this implies roughly 400 billion Jupiter mass rogue planets. And Jupiter mass rogue planets are the easier ones to detect. Smaller Earth mass rogue planets would be far more common if the standard mass distribution of planets applies. More recent analyses using larger datasets from the OGLE survey and incorporating shorter duration events consistent with smaller masses have pushed the estimates higher. Some analyses suggest that Earth mass rogue planets may be several times more common than stars, that there may be 1 trillion or more Earth mass free-floating planets in the Milky Way alone. These estimates are uncertain. The detection efficiency of microlensing surveys is not perfectly characterized. The interpretation of short-duration events is complicated by other possible explanations. The extrapolation from a sample of detected events to the full galactic population requires assumptions that may not be perfectly accurate. But even at the lower end of the estimates, the population is enormous. Hundreds of billions of free-floating planets, possibly more than 1 trillion, and some fraction of those planets have moons. How large a fraction? We do not know. We have never detected a moon of a rogue planet directly. The distances and the darkness make this extraordinarily difficult. But in our solar system, moons are common. Jupiter has 95 confirmed moons. Saturn has 146. Even Mars has 2, and there is evidence that many of the small bodies in the outer solar system have companion moonlets. If rogue planets retain a fraction of their original moon systems when they are ejected, and the models suggest they typically do, though the ejection process perturbs the moon orbit significantly, then there could be hundreds of billions of rogue moons in the Milky Way, possibly hundreds of billions in orbit configurations that generate significant tidal heating. The February 2026 paper found that between 12 and 15% of rogue moons in suitable orbital configurations experience tidal heating comparable to that of Europa and Enceladus, the solar system moons we consider most likely to harbor life. Apply that fraction to hundreds of billions of rogue moons and you get tens of billions of potentially habitable environments in the galaxy. Hidden in the dark, invisible to our current instruments, moving silently through the spaces between the stars. Tens of billions. Let's talk about what the surface conditions on a habitable rogue moon might actually be like. Not the abstract parameters, the temperature, the atmospheric pressure, the tidal heating rate, but the actual experience of being on such a world, if experience is even possible there. The temperature at the surface, according to the February 2026 models, could be anywhere from just above the freezing point of water, a few degrees Celsius, to significantly warmer, depending on the atmospheric thickness and the rate of tidal heating. Not comfortable by human standards, necessarily, but within the range of liquid water. Within the range where water chemistry can operate. The atmospheric pressure would be high. A thick hydrogen atmosphere providing significant greenhouse warming would exert substantial pressure at the surface. Not the crushing pressures of Venus, which has a surface pressure 90 times Earth's, but potentially several times Earth's atmospheric pressure, enough that the atmosphere would feel dense, would muffle sound, would alter the physics of weather. Weather, because a rogue moon with a liquid water ocean and a warm, dense atmosphere would have weather. Water would evaporate from the ocean surface. Water vapor would rise into the atmosphere, cool, condense into clouds, fall as rain or snow, run back to the ocean. The basic hydrological cycle, the cycle that shapes Earth's surface and drives much of its chemistry, would operate. In the dark, without sunlight to drive evaporation directly, the driving force for the hydrological cycle would be the temperature gradient between the warm tidal heated surface and the cold upper atmosphere. Convection, the rising of warmer, less dense air and the sinking of cooler, denser air, would power atmospheric circulation. Weather systems would form, move, dissipate. Storms might be common. The ocean itself would circulate. The tidal forces that heat the moon's interior would also drive ocean circulation. The temperature differences between ocean regions heated by submarine volcanic activity and cooler surface regions would create currents. The orbital period of the moon, the cycle of tidal stretching and relaxing, would drive tidal currents in the ocean. An ocean in the dark, circulating, mixing chemicals, providing a medium in which chemistry can happen continuously, without freezing, without desiccating, without the disruptions that would occur if the energy source were intermittent. Is this enough for life? We do not know. But on Earth, life appeared in the oceans within the first several 100 million years after the planet formed, quickly in geological terms. And it appeared in conditions that, in some ways, may not have been more hospitable than what we are describing on the rogue moon. Early Earth had a reducing atmosphere, perhaps rich in hydrogen and other gases. It had no ozone layer to protect against ultraviolet radiation. It had active volcanism and meteorite bombardment, and life appeared anyway, quickly, persistently, in forms that then spent 3 billion years exploring every available chemical strategy for extracting energy from the environment before eventually discovering the trick of using light directly, photosynthesis. On the rogue moon, photosynthesis is not available. But every other trick, chemosynthesis, using chemical gradients as an energy source, fermentation, extracting energy from organic molecules, every form of metabolism that does not require sunlight is potentially available. The chemistry is there. The energy is there. The liquid water medium is there. The one thing we cannot know from our vantage point in a solar system orbiting a star is whether life actually appeared on any of the habitable rogue moons that the calculations suggest should exist. But the calculations suggest the conditions for it are present. And that is something. Now let's think about what it would mean for the search for life in the universe if rogue moons are genuinely habitable. The standard framework for the search for extraterrestrial life focuses on stars. We survey stellar systems for planets in habitable zones. We look for biosignatures in the atmospheres of these planets using telescopes like Webb. We listen for radio signals from technological civilizations that may have developed on these worlds. All of this framework assumes that stars are necessary for life, that life requires the relatively stable, long-lived energy source that a main sequence star provides, that the habitable zone, the stellar habitable zone, is where the search should focus. If rogue moons are habitable, if liquid water oceans can exist for billions of years in the dark of interstellar space, then the stellar habitable zone is not the only place to look. It may not even be the most common place to look. Consider the numbers again. There may be hundreds of billions of potentially habitable rogue moons in the Milky Way. The number of planets in the stellar habitable zones of all Milky Way stars, while also potentially enormous, is constrained by the number of stars, approximately 200 billion, and the fraction of them that have habitable zone planets, estimated at perhaps 20 to 40%. That gives something like 40 to 80 billion stellar habitable zone planets. If the rogue moon estimate is even roughly correct, the number of potentially habitable rogue moons could match or exceed the number of stellar habitable zone planets. The galaxy may have two roughly comparable reservoirs of potentially habitable environments: the stellar habitable zones we have been focusing on, and the dark, invisible population of rogue moons we have largely ignored. This would fundamentally change the Fermi paradox calculation. The Fermi paradox, the question of why, in a universe presumably populated by life, we have detected no signal of it, rests partly on assumptions about how common habitable environments are. If the number of habitable environments is much larger than previously thought, the paradox becomes, if anything, more acute. More habitable worlds should mean more life, more civilizations, more signals. But we still hear nothing, unless the life on rogue moons, isolated in the dark with no star to point instruments toward, is simply not findable by the methods we are using. Unless the civilizations that might arise on rogue moons are surrounded by darkness with no obvious reason to broadcast into the void. Unless life in the dark is common and life that makes itself known is rare. This is a different kind of answer to the Fermi paradox. Not that life is rare, but that life is mostly invisible, hidden in the dark places we have not thought to look. Now let's go deeper into the physics of what keeps these worlds alive. Because tidal heating is not unlimited, and the lifespan of a rogue moon's habitability is not infinite. The orbital eccentricity that drives tidal heating is not permanent. Tidal forces not only heat the moon's interior, they also gradually circularize the orbit. Just as the heating converts orbital energy into thermal energy, the process gradually reduces the eccentricity of the orbit, bringing the moon's orbit closer to circular. As the orbit circularizes, the tidal heating decreases. Eventually, if the orbit becomes sufficiently circular, the tidal heating drops below the level needed to maintain liquid water, the surface freezes, and the habitability window closes. The timescale over which this happens depends on the properties of the moon, its size, its internal structure, its rigidity, and on the properties of the planet, its mass, and the orbital parameters of the moon. For the scenarios the February 2026 paper found most favorable, the habitability window is up to 4.3 billion years. But 4.3 billion years is not forever. It is a finite window, a window that opened when the planet was ejected from its star system and the moon's orbit was stretched into its eccentric configuration. A window that is now, for any given rogue moon, at some point in its progress toward closure. For the rogue moons that are still in their habitability window right now, the ones whose orbits are still eccentric enough to generate adequate tidal heating, whose hydrogen atmospheres are still thick enough to retain the heat, the conditions for life may exist at this moment. And for the ones whose habitability windows have already closed, whose orbits have circularized, whose tidal heating has dropped, whose surfaces have frozen, the life that may have developed during the window might still persist in subsurface oceans, kept liquid by the residual internal heat of the moon's formation and the decay of radioactive elements in its interior, long after the surface freezes. The habitability window for surface liquid water may close, but life, once established, may find ways to persist in the dark interior long after the surface is frozen. Life is persistent. On Earth, organisms have been found in environments that would kill an unprotected human in seconds, in the crushing pressures of the deep ocean, in the boiling acidic water of volcanic hot springs, in the frozen soil of Antarctica, in the intensely radioactive environments of nuclear reactor cores. Life adapts. Life finds a way to use whatever energy and chemistry is available. On a rogue moon whose surface has frozen, the remaining warm interior, the deep ocean beneath the ice, the hydrothermal systems where the residual interior heat drives water rock chemistry, would still be an environment where life could persist. Indefinitely, potentially, if the interior heat is maintained by radioactive decay rather than tidal forcing alone. A rogue moon that was once fully habitable at the surface, with open oceans, with weather, with complex chemistry, and that has since frozen over, might still harbor life in its deep, dark interior. Microbial life, almost certainly. Simple, hardy, chemosynthetic, but alive, and we would have no way of knowing. Let's talk about the specific physical scenario the February 2026 paper models in most detail, because the numbers are worth understanding concretely. The team focused on a moon roughly the mass of Earth, one Earth mass, one Earth radius, orbiting a free-floating planet in the mass range of a few to several Jupiter masses. The orbital period of the moon around the planet was taken to be between a few days and a few weeks. The orbital eccentricity, the key parameter controlling tidal heating, was varied across a range of values. For an Earth-mass moon with an orbital eccentricity of approximately 0.1, meaning the moon's orbit is slightly elongated, with the closest approach to the planet about 10% closer than the furthest, and a thick hydrogen atmosphere of approximately 10 times Earth's atmospheric pressure, the surface temperature at equilibrium was found to be above the freezing point of water. Not by a huge margin. The surface temperature in the best scenarios was perhaps 10 to 30 degrees Celsius, cool by tropical standards, but within the range of liquid water. Within the range where complex chemistry operates, where organic molecules are stable, where the biochemistry we know is possible. The tidal heating rate required to achieve these temperatures is approximately 0.04 watts per square meter of surface area, a little less than half the rate of tidal heating on Jupiter's moon Io, which is one of the most intensely tidally heated bodies in the solar system. This is a moderate amount of tidal heating, well within the range that the orbital parameters considered can provide. The hydrogen atmosphere of 10 times Earth's atmospheric pressure is dense but not absurdly so. It is comparable to the atmospheric pressure at the bottom of Earth's ocean at a depth of about 90 meters, significant, but not crushing. At the surface of a rogue moon, you would feel the pressure as significant, more than double what a diver experiences at recreational depths, but not immediately lethal. The combination of these parameters, moderate tidal heating, thick hydrogen atmosphere, Earth-mass moon around a Jupiter-mass rogue planet, gives the habitability window of up to 4.3 billion years. What is notable about this is that none of these parameters are extreme. They do not require fine-tuning. They do not require unusual or coincidental combinations of properties. They are within the range of what we would expect to find in a significant fraction of rogue moon systems, based on what we know about moon formation and orbital dynamics. The habitability of rogue moons is not a fringe possibility requiring exotic conditions. It is a consequence of straightforward physics that applies to a significant fraction of the rogue planet population. This is what makes the paper's conclusions so potentially significant. It is not a story about one unusual scenario. It is a story about a class of objects that may be extraordinarily common, in conditions that the physics says should frequently support liquid water, for timescales long enough for complex life to evolve. Let's now ask the question that the entire story has been building toward. Is anything actually living on these worlds? The honest answer is we do not know. We have no observations of rogue moons. We have no data from these environments. We cannot currently detect them, let alone characterize their conditions or search for biosignatures. What we have is physics. We have calculations showing that the conditions for liquid water, which we take as a necessary condition for life as we know it, can be met on rogue moons for billions of years. We have the analogy of Earth, where life appeared in liquid water relatively quickly after the water became available. We have the principle that chemistry operates wherever the conditions allow, and that life is a specific type of self-sustaining, self-replicating chemistry. None of these things guarantee life on rogue moons. Life might require conditions more specific than liquid water and a chemical energy source. The origin of life might be a rare event that requires specific circumstances beyond what we know. The emergence of life on Earth might have been a statistical fluke, something that happened once in the history of the solar system by chance rather than necessity. If life requires extraordinary luck to originate, then most habitable environments will be lifeless. Most of the potentially habitable rogue moons will be dark, lifeless, liquid water oceans with no biology. But if life emerges wherever the conditions are right, if the origin of life is something that chemistry does naturally, given liquid water and chemical energy and sufficient time, then the rogue moons are not empty. They are populated, not with anything that looks like us, not with anything that has ever seen a star, not with anything that could make a radio signal we might detect or build a spacecraft that could leave its world and travel to ours, but with life, with the chemistry of self-replication and metabolism, with organisms that have spent billions of years adapting to an environment of darkness, pressure, tidal flexing, and chemical gradients, with ecosystems built entirely on the energy of their planet's gravity, in oceans that have never been touched by starlight. The question of whether life is there is the deepest unanswered question in astrobiology. It is a question that cannot currently be answered by any instrument we have. It is a question whose answer would change everything we think we know about life in the universe. And the February 2026 paper is telling us that the question is worth asking, that the environments are there, that the physics says they could be habitable, that we should take seriously the possibility that life exists in the darkest, most inaccessible, most counterintuitive places in the galaxy. Now let's talk about whether we could ever find these worlds. Because the habitability is one question and the detectability is another. Current rogue planet detection relies almost entirely on gravitational microlensing. When a rogue planet passes in front of a background star, the star briefly brightens as the planet's gravity bends the star's light toward us. The duration of the brightening encodes the planet's mass, and the shape of the light curve contains information about the planet's properties. But microlensing events are brief, hours to days for Earth mass objects, weeks for Jupiter mass objects, and they cannot be predicted in advance. The planet has to happen to pass in front of a background star from our exact line of sight. And during the brief event, the information that can be extracted about the planet is limited. Detecting a moon of a rogue planet through microlensing would require the moon to also pass in front of the background star in a specific geometric configuration, or to affect the shape of the light curve in a detectable way. This is theoretically possible, but has not yet been demonstrated observationally. The Nancy Grace Roman Space Telescope, scheduled for launch in September 2026, is specifically designed to conduct a large-scale microlensing survey of the galactic bulge. It will monitor hundreds of millions of stars simultaneously, watching for the brief brightenings that signal the passage of a massive object. Its survey is expected to detect thousands of free-floating planets, dramatically increasing the known population and providing the first robust statistical characterization of the rogue planet mass function. Whether Roman can detect the moons of rogue planets, whether its photometric precision and cadence are sufficient to see the subtle perturbations in a microlensing light curve produced by a moon, is an open question. Some theoretical analyses suggest it might be possible for favorable configurations. A confirmed rogue moon detection by Roman would be an extraordinary discovery. Direct detection of a habitable rogue moon, actually pointing a telescope at one and characterizing its properties, requires technology that does not yet exist. A rogue moon is dark. It emits thermal radiation in the infrared, corresponding to its surface temperature. At perhaps 10 to 30 degrees Celsius, it emits most strongly at wavelengths around 10 micrometers in the mid-infrared. But at interstellar distances, this thermal emission is extraordinarily faint. Even Webb, the most sensitive infrared telescope ever built, could not detect the thermal emission of an Earth temperature body at even the nearest interstellar distances without knowing exactly where to point. If we could identify a rogue planet system through microlensing, if Roman detected the lensing event and the light curve suggested the presence of a moon, we might be able to follow up with deeper observations using Webb or its successors, perhaps detecting the thermal emission of the moon if it is warm enough and close enough. This is a long chain of ifs. Microlensing detection, then light curve analysis suggesting a moon, then follow-up characterization of the moon's thermal properties. Each step is difficult. The whole chain has never been accomplished, but it is not physically impossible. The barriers are technological, not fundamental. Better instruments, better surveys, better analytical tools. These are engineering challenges, not violations of physical law. The rogue moons may be findable eventually. The physics does not forbid it. The question is whether we will build the instruments and develop the techniques needed to find them before we give up looking. Let's go somewhere unexpected. Let's think about what it would mean for intelligence to develop on a rogue moon. This is speculative, very speculative. We are several steps beyond what the February 2026 paper actually claims. It claims only that surface liquid water can be maintained, not that complex life is likely, and certainly not that technological intelligence could emerge. But speculation, carefully conducted, is valuable in science. It helps us identify questions worth asking and scenarios worth modeling. So imagine that life did appear on a rogue moon billions of years ago. Imagine that it followed something like the trajectory life has followed on Earth, from simple self-replicating chemistry to increasingly complex organisms, from single cells to multicellular organisms, from organisms without nervous systems to organisms with them, from simple neural circuits to complex brains. Imagine that intelligence emerged. What would that intelligence be like? What would it know? What would it want? It would know nothing of stars. Not because stars are invisible from the rogue moon. In principle, the stars of the galaxy would be visible as faint points of light even through a thick atmosphere, assuming the atmosphere is at least partially transparent to some wavelengths. But the stars would be distant, faint, and seemingly irrelevant to the immediate environment. The sky would be dark. The world would be ocean, atmosphere, darkness. The intellectual history of an intelligent species on a rogue moon might not include astronomy in any early form. The sky offers little to organize around, no sun rising and setting, no moon. The planet fills the role of moon, but does not move in the same way from the surface of its moon. No seasons driven by orbital mechanics around a star. The rhythm of the world would be tidal, the subtle flexing of the ground as the orbit carries the moon closer to and further from the planet, the slow seasonal variation if the planet's orbit has any precession or variation. A civilization on a rogue moon would develop chemistry before astronomy, physics of materials and fluids before celestial mechanics, the study of their ocean before the study of the stars. When they eventually developed astronomy, when they built instruments sensitive enough to see the galaxies and measure the distances to stars, the discovery that they were not orbiting any star would be one of the strangest moments in their intellectual history. A civilization that grew up assuming they were simply on a world, a water world in darkness, discovering that they were adrift, that no star was theirs, that they were wanderers in the dark spaces of the galaxy, moving through a void that most inhabited worlds never enter. The existential weight of that discovery, of learning that your world is not anchored, not part of a stellar system, not in the web of planetary relationships that most habitable worlds presumably participate in, is difficult to imagine. And then, perhaps, the further discovery that other worlds, the worlds around stars, were not like their world, that those worlds were warm and lit, that their surfaces received energy from a star rather than from the interior of a planet, that the chemistry of those worlds was driven by photosynthesis rather than chemosynthesis. The encounter between a civilization from a rogue moon and a civilization from a stellar system, if it ever happened, would be an encounter between two fundamentally different experiences of what a world is. Two different answers to the question of what a habitable environment looks like. We assume, in our stellar-centric thinking, that life from stellar habitable zones would be recognizable to us in some ways, that it would have some broadly analogous experience of seasons, of a sky with a sun, of light and dark and cycles driven by stellar energy. A rogue moon civilization would share none of these features. It would be alien in the deepest sense, not just in its biology, in its fundamental experience of what existence is. Let's come back to what we know, to the solid ground of the physics. The February 2026 paper is a theoretical study. It models conditions, calculates temperatures, determines whether liquid water is stable. It does not detect any rogue moons. It does not find any life. It does not claim that intelligent civilizations exist in the dark. What it claims is that the physical conditions for liquid water, widely accepted as a necessary condition for life, can be maintained on some fraction of rogue moons for billions of years through the combination of tidal heating and hydrogen atmospheric greenhouse warming. This is a significant claim. It extends the range of potentially habitable environments in the galaxy beyond the stellar habitable zones that have dominated astrobiological thinking. It suggests that the search for life should not be restricted to the neighborhoods of stars. It joins a growing body of evidence that liquid water, and therefore potentially life, can exist far outside the traditional habitable zone. Subsurface oceans on Europa and Enceladus, heated by tidal forces from Jupiter and Saturn respectively, are the solar system examples. Ocean worlds, planets covered by deep global oceans, may be common in stellar systems beyond the classical habitable zone, kept warm by internal radioactive decay or tidal heating rather than stellar irradiance. And now, rogue moons, kept warm by tidal heating alone in the complete absence of any stellar light. The universe, it seems, is more creative about providing liquid water than our models initially assumed. Life's most fundamental requirement turns out to be less dependent on stellar energy than we thought. Internal energy, tidal, radioactive, geothermal, can substitute for stellar energy in ways that allow liquid water to persist in a far wider range of environments. If life requires only liquid water and chemical energy, and we have no strong evidence that it requires more than this, though we also cannot be certain, then the number of potentially habitable environments in the universe may be vastly larger than the number of stellar habitable zone planets. The universe may be full of dark, warm, wet worlds, hidden, invisible, moving through the spaces between the stars in silence. And we have only just begun to understand that they might exist. Let's think about what Earth's own future might tell us about rogue worlds. Because there is a version of Earth's story that ends with Earth becoming a rogue world. In approximately 5 billion years, the sun will expand into a red giant. Earth's surface will be sterilized. The oceans will boil. The atmosphere will be stripped by the solar wind. Whatever life exists on Earth at that time, whatever form it has taken over 5 billion more years of evolution and change, will be destroyed. The planet itself will survive, probably. Even if the expanding sun engulfs Earth's orbital path, Earth-mass planets have been found orbiting white dwarf stars. They apparently survive the red giant phase in many cases. A scorched, airless, geologically dead rock might remain at roughly Earth's current orbital distance when the sun completes its evolution to a white dwarf. But imagine a different scenario. Imagine that in 4 billion years, before the sun expands and sterilizes Earth, a passing star has a close gravitational encounter with the solar system. The encounter disrupts Earth's orbit. Earth is flung outward, past Mars, past Jupiter, past the outer planets, into the dark. Earth, with whatever life it hosts at that point, becomes a rogue planet. The oceans would freeze within decades. The atmosphere would freeze onto the surface over centuries. Life on the surface would die. Life in the deep ocean at hydrothermal vents might persist for much longer, kept warm by Earth's interior heat, by the radioactive decay of uranium and thorium deep in the mantle for millions or billions of years. Earth becoming a rogue world is not likely. The probability of a sufficiently close stellar encounter in the next 4 billion years is small. But it is not impossible. And the scenario illustrates something important. Life once established is hard to kill. Earth's biosphere has survived 5 major mass extinctions, each of which killed the majority of species on the planet. It has survived asteroid impacts, volcanic eruptions on scales that produced global climate crises, ice ages that covered much of the planet in ice, and the transition from an anoxic atmosphere to an oxygen-rich one. A transition that was itself a mass extinction event for the anaerobic organisms that dominated before photosynthesis evolved. Life on Earth has been adapting and persisting for nearly 4 billion years. If Earth were to become a rogue world, some of that life, the deep subsurface microbial communities, the hydrothermal vent ecosystems, would likely persist for millions of years in the warm interior. A rogue Earth would be dark at the surface, frozen, but inside, in the warmth of its own radioactive interior, things would still be alive. Now extend this thought to the rogue planets that actually exist. Many of them were presumably ejected from their star systems early in their stellar system's histories, before life had time to develop, or before planetary conditions were hospitable. But some may have been ejected later. Some may have been ejected from systems that had already developed life. A rogue planet that was ejected with life already aboard, carrying microbial ecosystems in its subsurface ocean, carrying the seeds of whatever biology had developed in the billions of years before ejection, would carry that life into interstellar space. Not to survive on the surface, which would freeze, but to persist in the interior, kept warm by whatever internal heat remained. This is a form of panspermia, the hypothetical transfer of life between worlds, that does not require the extraordinary conditions usually invoked, like life surviving in meteorites or on comets. A rogue planet carrying its own ocean of life, migrating through the galaxy, is a vastly more hospitable vehicle for life than a meteorite. Could a rogue planet, carrying life from its birth system, eventually encounter another stellar system? The probability is very low. Stellar systems are rare in the vast spaces between the stars, and rogue planets move slowly enough that encounters are extraordinarily infrequent. But the galaxy is 13 billion years old. Over 13 billion years, even very low probability events can accumulate. Life may travel between the stars on rogue worlds, slowly, over billions of years, in the dark. Let's go back to the night sky above you right now. In the direction of the galactic center, roughly where the constellation Sagittarius rises in the summer sky, the density of stars is highest. And in those dense stellar fields, the density of rogue planets is also likely highest. More stars means more stellar systems, more planetary formation, more gravitational encounters, more ejections. Somewhere in that direction, many of them spread through the galaxy, rogue planets are drifting. Most are cold and dead. Some are warm, wrapped in hydrogen atmospheres, orbited by tidally heated moons with liquid water oceans. And in some of those oceans, something might be moving, not swimming the way fish swim necessarily, not anything with a spine or a brain or anything recognizable as the kind of life that evolved on Earth under starlight, but something, chemistry that sustains itself, that replicates, that evolves, that has been adapting to the specific conditions of its dark, warm, pressurized, tidally flexed world for billions of years. Something alive, in the dark, with no knowledge of the sun. No knowledge of the stars, except as faint lights in a sky they may never have looked at, because the sky offers nothing relevant to survival in an ocean. Something that has never seen starlight, that lives in a world defined by pressure and chemistry and the rhythmic squeeze of gravity, that has been alive or whose ancestors have been alive since before the Earth existed in its current form. If this is real, if life exists on rogue moons, then the universe is more populated than we thought. Not populated with civilizations sending radio signals, not populated with beings who look up at the stars and wonder, but populated with the basic fact of life, of chemistry that has bootstrapped itself into the self-sustaining, self-replicating, energy-harvesting thing that we call alive. And we have no way to know, not yet, not with current instruments, but the physics says it could be there. And physics has a good track record of being right about what exists in the universe, even before we can see it directly. The rogue moons are out there. The liquid water is potentially there. The chemistry is potentially there. Whether life is there is the question the universe is keeping to itself. For now, let's spend some time on what this discovery changes about how we should think about the search for life. For decades, the search for extraterrestrial life has been organized around a specific set of assumptions. Life requires a star. Life requires a planet in the habitable zone of that star. Life requires liquid water maintained by stellar irradiance. Therefore, search the stellar habitable zones. These assumptions are not wrong. They are a reasonable first approximation, based on the one example of life we know, Earth, orbiting the Sun in the middle of the stellar habitable zone. And the search for life in stellar habitable zones is absolutely worth pursuing. The James Webb Space Telescope study of exoplanet atmospheres in habitable zones is potentially one of the most important scientific programs in human history. But the February 2026 paper, building on earlier work on Europa, Enceladus, and other ocean worlds, adds a category of potentially habitable environments that the stellar habitable zone framework entirely misses. Environments that are not in any stellar habitable zone. Environments that have no star at all. The implications for how we search for life are significant. If life can exist on rogue moons, then biosignatures, chemical signs of life, might be present in environments we are not currently designed to detect. The characteristic atmospheric signals that Webb looks for, oxygen, methane, water vapor, dimethyl sulfide, are biosignatures in the context of a planet bathed in stellar light, where photosynthesis can drive atmospheric chemistry to specific disequilibrium states. The same biosignatures may not be produced by life in a dark, hydrogen-dominated ocean environment. The biosignatures of life on a rogue moon might be entirely different from the biosignatures we are looking for. They might be signatures of chemosynthetic rather than photosynthetic metabolism. They might be detectable in the infrared thermal emission of the moon rather than in the reflected spectrum of stellar light. They might require entirely different detection strategies that we have not yet developed. This is not an argument against the current search for life. It is an argument for broadening it, for developing new detection strategies capable of finding biosignatures in dark, tidally heated environments, for including rogue world science in the portfolio of astrobiology programs. The universe offers more habitable environments than we thought. Broadening the search to include them is a scientific imperative, not a fringe activity. Right now, tonight, as you listen to this, the galaxy is doing what it has always done. Stars are forming in molecular clouds. Planets are assembling around those stars. Some of those planets are being ejected in the gravitational chaos of early solar system formation. Some of those ejected planets are carrying moons. Some of those moons have orbits that were stretched into eccentric configurations by the ejection event. Some of those moons have thick hydrogen atmospheres. And somewhere in the spaces between the stars in the darkest parts of the galaxy, some of those moons have liquid water oceans. Warm, dark, moving. Whether anything swims in those oceans is the question. The universe is old enough. The chemistry is available. The physics says the conditions can be met for the timescales life requires. We are the first species we know of to have looked at the universe carefully enough to ask this question, to have built the tools to see the stars, measure their distances, study the physics of tidal heating, calculate the surface temperatures of moons orbiting hypothetical rogue planets in interstellar space, and conclude that liquid water might be there. That capability, the ability to reason about environments we cannot visit, using physics we derived from our experience of one world around one star, is one of the more remarkable things about being the kind of life we are. We can imagine the dark oceans of the rogue moons. We can calculate their temperatures. We can model their chemistry. We can ask whether anything lives there. We cannot yet answer that question, but asking it is the first step. And the universe, patient and vast and full of things we have not yet found, is waiting for us to build the instruments that might, one day, begin to answer it. The dark places are not empty, or at least the physics says they might not be. Sleep well. For those still listening, in the quiet between waking and sleep, my biggest goal on this channel is to reach 1,000 subscribers. So if you enjoy falling asleep to my videos, please hit that subscribe button. We continue. There is something worth thinking about as the boundary dissolves. The world you live on, this specific planet, with its specific oceans and its specific atmosphere and its specific star, is one kind of world. It is the kind of world we have organized all of our thinking about life around. Warm, lit from above, driven by stellar energy, cycling water from ocean to cloud to rain and back. But this is not the only kind of world that might harbor life. The universe appears to be more creative than our models assumed. Ocean worlds heated from within. Moons of rogue planets kept warm by tidal forces in interstellar dark. Subsurface oceans beneath ice shells on bodies that receive no stellar light worth measuring. The common thread in all of these is liquid water and chemical energy. Not sunlight, not the specific conditions of Earth, just liquid water and chemistry. If that is truly all that life requires to originate, and we do not know that it is, but we have no strong evidence that it requires more, then the universe is full of life in ways that our stellar-centric thinking has caused us to underestimate. Full of life in the dark, under ice, in the deep interiors of worlds moving silently through the spaces between the stars. None of it like us, almost certainly. None of it looking back at us across the dark. None of it building instruments to search for signals from distant beings on stellar habitable zone planets, but alive in the fundamental sense. Chemical, self-sustaining, evolving, adapting. The night sky above you is vast. The spaces between the stars are vaster. In those spaces, in the dark that no telescope has yet illuminated, the rogue worlds drift, and some of them are warm inside. And in that warmth, something might be moving. You are not surrounded by emptiness. You are surrounded by a galaxy that is older than the sun, more complex than any model has captured, and more full of life, possibly, than any generation before yours had reason to suspect. The dark is not empty. It never was. Sleep well.